Welcome back, everyone. We're diving into an interesting challenge that faces large language models today, and that's handling longer and longer sequences of information. It's a bit like asking someone to remember every single word they've ever read in their entire life.
Yeah, tough.
All right. Well, that's where a language model's key value cache comes in. You can kind of think about it like the model's working memory.
Yeah, and the thing is that this memory, the KV cache, it grows proportionally to the length of the text you feed it. So as you might imagine, it quickly becomes a bottleneck when you're dealing with really massive amounts of data.
I can imagine.
Yeah, and there have been quite a few attempts to address this, like compressing the information that's stored in that cache. But a lot of those attempts, they often come with some performance trade-offs.
Mhm.
You save memory, but you lose processing power.
So it's like a balancing act.
Yeah.
So where does that lead us?
Well, this is where Tensor ProducT ATTenTion, or TPA, enters the picture.
Yeah.
This is a new method that was described in a research paper by Yufan Zhang and his colleagues. And it offers, I think, a really elegant way to represent those core components of attention. The queries, keys, and values, but in a much more compact way.
Oh, that's interesting.
Yeah.
So how does TPA achieve that?
So TPA achieves this by breaking down those components, the queries, keys, and values, into smaller, simpler pieces.
Uh-huh.
And it uses a technique called tensor decomposition to do that. It's a little bit like finding the most basic building blocks of, say, a Lego structure so that you can then reconstruct that entire structure, but just with those essential blocks.
Okay, that makes sense. So it's about finding the most fundamental pieces of information and then using those to rebuild the whole thing.
Right. And what I think is particularly remarkable about TPA is that it doesn't just compress information indiscriminately. It actually adapts to the specific context of whatever text is being processed.
Oh, yeah.
So it can represent the most relevant information with even greater accuracy.
That's clever. So it's not just squeezing everything down, it's figuring out what's important and focusing on that.
Right.
So how do you actually put this into practice?
Well, the researchers, to demonstrate this, they went ahead and they developed a new transformer model architecture. They call it T6. And it's specifically designed to use TPA.
Okay, so they built a whole new model around this concept.
And did it work?
Well, in their experiments, what they found was that T6 outperforms traditional transformers on language modeling tasks. So specifically, it's better at predicting the next word in a sequence,
Uh-huh.
which is a pretty key indicator of how well the model actually understands language.
Right, because if it can predict the next word, it means it's grasping the meaning of what's come before.
Exactly. And it actually, they found that it also improves performance in downstream tasks like question answering. So it has real-world applications as well.
That's impressive. So it's not just a theoretical improvement. It actually makes these models better at what they do. Yeah. And another interesting aspect of TPA is that it's compatible with rotary position embeddings, or ROPE, as it's called.
ROPE.
Yeah, it's a technique that's used to encode the position of words within a sequence. And TPA integrates really seamlessly with ROPE,
I see.
which is actually something that previous memory-saving techniques struggled with.
So it's kind of solving multiple problems at once.
Yeah, it seems so.
So if I understand correctly, TPA is not only more efficient, but it also plays well with existing techniques.
Yeah, and the researchers actually also uncovered a surprising link between TPA and other existing attention mechanisms that are already out there.
Like what?
So it turns out that TPA isn't just a brand new technique, it actually provides a kind of unifying framework for understanding other mechanisms like multi-head attention,
Oh, interesting.
multi-query invention, and even that more recent grouped query attention.
Okay, so it's almost like finding a common ancestor.
Right. It's almost like these familiar techniques. You can see them as specific instances or maybe special cases of this more general TPA framework.
I see. So it's like TPA is the parent and all these other techniques are the children.
Right. It's like discovering that seemingly different species are all variations on a single evolutionary theme.
Wow, that's a pretty profound insight. So bringing it back to that initial memory issue we talked about, how much can TPA actually help with that?
Well, the researchers have shown that TPA can dramatically reduce the memory footprint of the KV cache. And we're talking about a factor of 10 or more compared to those standard attention mechanisms.
10 times smaller. That's incredible.
Yeah.
So it's like shrinking an entire library down to the size of a single bookshelf.
Yeah, that's a good analogy.
So that has huge implications for what these language models can do in the future, right?
Absolutely. It opens up the possibility of handling much longer and more complex texts than ever before. So to really get a feel for how powerful this TPA is, we should look at some of the experiments that the researchers did. So they tested out this T6 model that they made on a huge text data set called FineWeb Edu. It's got like 100 billion tokens in it.
Wow, that's enormous.
Yeah, it's a lot of data. And they compared T6's performance to other models that were using different attention mechanisms, like those ones that we talked about, the multi-head attention, the multi-query attention, and the grouped query attention. And they even threw in that memory-efficient linear attention to see how it would stack up.
Okay, so good range of models to compare against.
Right. And the results are pretty striking. Across the board, TPA had consistently lower perplexity scores, which means it's better at predicting that next word in a sequence.
Right, right.
And it wasn't just limited to language modeling either. This improvement also showed up in those downstream tasks as well. So it really shows you that it has a real-world impact.
That's great. So it's not just some theoretical, improvement. It actually makes a difference in how well these models perform on real-world tasks.
Yeah. And one of the things that I found really compelling was the memory usage. So in some cases, TPA was using 5 or even 10 times less memory for that KV cache.
Wow, that's a significant reduction.
Yeah.
I mean, I can imagine that being really crucial for scaling up these models and making them more practical to use.
Yeah, and to help really visualize this efficiency, the paper has a figure in it. It compares the training and validation loss curves for the different models on that FineWeb Edu data set. And what's interesting is the curves for TPA and that TPA K-Vonley variant, they converge much faster.
Oh, I see.
And they also have lower losses compared to those baseline models.
So visually, you can actually see that the TPA-based models are learning more effectively.
Right, and they're generalizing better to that unseen data.
That's fascinating. So it's not just about memory, it's about better learning as well.
Yeah, exactly. And to kind of hammer home that point, the researchers put together this table that summarizes all the evaluation results. And it shows how those different models performed on various benchmarks.
Okay, so we can directly compare TPA to the other mechanisms across a whole bunch of tasks and model sizes. That's a lot of data to look at.
Right. And the data from this table just confirms that TPA really is a strong contender. It's achieving competitive or even better results in both those zero-shot and few-shot settings.
Okay, so regardless of how much training data is available, TPA is holding its own.
Yeah. And what I also found impressive was how consistent TPA's performance is across all those different model sizes. It suggests that this approach is really robust and can scale well.
That's a good sign. So it's not limited to small-scale experiments. It can potentially work on much larger models as well.
Yeah, and the researchers didn't just stop at one single version of TPA. They actually explored all these different variations. They fine-tuned the factorization techniques and adapted TPA so that it would mesh with different parts of the model's architecture.
So they were really trying to optimize this for different scenarios.
Right.
That's pretty cool.
Yeah, and I think it highlights the flexibility of this approach. It's not like a one-size-fits-all solution. It's more of a framework that can be customized to fit whatever needs or constraints you have.
That makes a lot of sense. So it's not about saying, here's TPA, use it everywhere. It's about saying, here's TPA, adapted to your specific problem.
Exactly. And the paper actually concludes by acknowledging that TPA is really just one step forward in this ongoing pursuit of more efficient and powerful language models.
And they didn't stop there, right? They dug a bit deeper.
Yeah, they did. They looked at one variation that focuses just on factorizing those keys and values, but leaves the query projection the way it was.
Okay, so just focusing on specific parts of the attention mechanism.
Yeah. And this variant, they call it TPA K-Vonley, and it really shows you how targeted this approach can be with efficiency. So instead of trying to overhaul that whole model architecture, they just zeroed in on those parts of the attention mechanism that were using the most memory.
Clever. And did it work?
It seems like it. Their results showed that TPA K-Vonley can be just as effective as the fully factorized TPA, especially when you're working with those bigger models.
So focusing on the memory-intensive parts was enough to get similar benefits.
Yeah. And they also explored the potential of sharing those token dimension factors between the keys and values.
Okay, so streamlining things even further.
Right. And it ends up minimizing those memory demands even more. So it could be a really promising direction, especially for certain tasks.
So it sounds like there's no one-size-fits-all answer when it comes to implementing TPA.
Yeah, that seems to be the case.
It's more about finding the right configuration for your specific needs.
Yeah, I think the researchers really encourage experimentation, try different things out, see what works best for your particular task or your particular model.
It's about customization. That's
Yeah,
a good
yeah.
takeaway.
Right.
So I guess looking back at our deep dive here, we've learned a lot about this intricate world of attention mechanisms
Yeah, we have.
and some of the big challenges they face when we're dealing with these super long sequences and language models. But it seems like TPA offers a pretty promising solution.
Yeah.
It's really about streamlining how information is represented, making
Hmm.
it way more efficient. And who knows what the future holds? TPA is still relatively new to the scene, but it seems like it has the potential to really change things up in natural language processing.
For sure. I think this is just the beginning.
Yeah. Well, on that note, I think we'll wrap up our deep dive for today. So until next time, keep exploring, and we'll see you back here soon.